Hello everyone, this is Wangda Zuo. I'm a professor at Pennsylvania State University in the United States. I'm directing the Sustainable Buildings and Societies Laboratory. Today, I will give you an introduction about modeling in building-to-grid integration. This seminar is based on our book chapter 17 in the book Building Performance Simulation for Design and Operation. So the course includes my former and current PhD students, Sen Huang at Pacific Northwestern National Laboratory, Tom Sevilla at the University of Miami. In this seminar, we will first discuss the challenges faced by the power grid in area of renewable energy. And then, as a potential solution, we will introduce building-to-grid integration. After that, we will discuss the system modeling to enable building-to-grid integration. We will then demonstrate the usage of system modeling for building-to-grid integration, use two case studies. At the end, we will summarize what we have learned in today's seminar, and also recommend a few papers and books. To mitigate the climate change issues, people are adopting more and more renewable resources in our electricity generation. For example, the left figure shows the percentage of renewable resource in the U.S. electricity grid in 2015. The right figure shows the projected percentage in 2030. As we can see, in most of states, the percentage of renewable resource is going to be doubled in 15 years. In some states like California or Nevada, the percentage of renewable will be more than 50% of our total electricity generation. On one side, it is good to use more and more clean energy, but on the other side, this high penetration of renewable resource will also bring challenges to our future power grid operation. For example, there are many uncertainties when we're forecasting available renewable energy resource. As we can see from this figure, the data from the Middle Continental Independent System Operator in 2019 shows that when they do the day-ahead prediction, they overpredict the available renewable energy resource for 3,180 megawatts. This huge prediction error will make the operation of power grid very challenging. Another challenge is brought by the net zero energy building or community with on-site renewable energy generation. So, for example, this slide shows a net zero energy community in Florida named Historic Green Village. So the white figure shows the net load of this community in the past 4 years. The top blue color indicates the community is able to produce more energy than its consumption, therefore it exports the electricity back to the grids. The pink at the bottom shows the community needs more energy than its production, therefore it has to take energy from the grid. As you can see, the export-import of electricity from the community is highly fluctuating and changing over season. When we aggregate the millions of net zero energy buildings, we are going to see an interesting California Dagger curve predicted by the grid operator for California. This figure shows the net load curve from 2012 to 2020. As we can see, the significant change is for the afternoon portion, that the net load of the entire California is significantly reduced from 2012 to 2020 because the increased renewable energy, especially PV production. And then when the sun goes down, there's a very quick increase of the net load because the quick drop of PV production. This is going to bring two significant challenges. The first one is how to prevent the overgeneration of electricity in the afternoon. The second is how to quickly ramp up the energy production in the early evening to meet the demand. To address the challenges brought by high renewable penetration, on one side, the power grid community is trying different solutions. On the other side, we can use buildings to provide service to power grids. This is because of three reasons. First, buildings are the largest user of electricity. For example, they account for nearly 75% electricity usage in the U.S. Second, nearly 25% of buildings related usage are flexible. Third, the building management systems are ready for demand manipulation. The right figure shows the power flexibility of commercial building cooling systems in 14 different climate zones in the U.S. By adjusting the temperature set points for cooling, we will be able to increase the power demand by nearly 50 gigawatts, or decrease the power demand by nearly 40 gigawatts. To explore buildings' potential for power grid service, people propose the concept of building-to-grid integration, or B2G. There are many definitions about building-to-grid integration. In our view, building-to-grid integration employs buildings as already deployed, cost-effective solutions for passive energy storage. So this can be applied into two phases. In the design phase, buildings can be considered as a low-cost energy storage solution for economic design. In the operation phase, buildings can be employed for filter uncertainties from the supply side to balance the power grid. The U.S. Department of Energy website has comprehensive information about building-to-grid integration. You can visit the website using the link provided here. Next, we will focus on the modeling needs and requirements in building-to-grid integration. We will discuss this in three different stages: design, evaluation, and deployment. To apply B2G in the design stage, the first thing we need to do is set a goal. Here is to estimate the power flexibility the buildings can provide. As we can see from the right figure, the delta P high is the amount of power demand we can increase when needed. So this is P max, which is the maximum power demand, minus P base, which is the baseline power demand. So the baseline is we don't apply any B2G control. Similarly, we can estimate the power demand we can reduce using delta PL, which is P minimal minus P base. Here, P minimal is the minimum power demand required by the building to maintain the service. To estimate the delta P high, we need to calculate P max. Here, we can treat it as an optimization problem. So the power P is a function of three inputs. The first is Cu, which is controllable factor, such as room temperature set points. Then the U here is uncontrollable factors, such as weather condition, and X here is state of the system, for example, current room temperature. So this optimization has to satisfy a constraint, which is the G here. So this is the quality of service provided by building. For example, maintain the room temperature at a desired value or range. By solving this optimization problem, we can calculate the maximum P, while still maintain the service quality. Similarly, we can calculate the minimum P by using the optimization function and then again trying to satisfy the service quality. In the previous step, we set the goal by estimate the power flexibility we're able to provide. In this step, we're going to meet the goal by achieve the promised power flexibility with minimal negative impacts. We can treat this again as an optimization problem. The omega here is the negative impact by doing the B2G. Here our goal is to minimize this negative impact under the constraint of building service so that we are able to achieve the PDS, which is the desired power usage. Now, let's see what kind of models we needed to support the application in the design stage. First, we want to introduce the definition of system modeling, which is a mathematical way describing the relationships between inputs and outputs based on the theoretical knowledge or empirical insights. To apply system modeling for B2G, in the design stage, there are two major requirements. The system models should be able to run quickly with limited computing resource. This is necessary for enabling real-time control via various computing platforms, from a single board computer to a high-performance workstation computer, used by different building control systems. It is also preferable if a system models can provide derivatives of the object functions. So the key of the building-to-grid integration is to solve optimization problems, as I mentioned earlier. We can use derivative-based optimization algorithms if the system models can provide derivative of the object functions. Compared to the derivative-free algorithms, the derivative-based algorithms often have better performance in terms of computing cost and finding the global optimal solution. After we designed the B2G strategy, the next step is to evaluate this strategy. So to evaluate the B2G strategy, we will need to realistically represent the operating conditions of the system. In practice, we can use field test or virtual testbed, which is based on system modeling. So now let's focus on system modeling. To do that, first, the system models should have sufficient fidelity according to the evaluation objective. So this is because a faithful representation of the required operating conditions is crucial for the evaluation. Therefore, we should define the model fidelity to provide the necessary details and accuracy in responding operating conditions. Requiring more details of the system operating conditions often leads to higher fidelity models. Second, it is preferable to have building models that can be coupled with grid models. Since control strategies impact both the buildings and the grid, having both of them in the system modeling allows studying their dynamic interaction. To couple the building and the grid models, some new content should be considered in the building models. For example, the voltage and the current should be treated as inputs when evaluating building's response to the grid. So next, for real-world deployment, we need to utilize control strategies which can generate control actions in advance. In order to make control actions ahead of time, we need to predict future building operating conditions. To do that with system modeling, there are two requirements on modeling. First, the temporal solution of the prediction should be determined based on the goal of the control strategies. Take the prediction of the solar radiation as example. If the deployed strategy aims to limit the studied system's power demand from the grid over a 15 minutes interval, a minute-level prediction may be sufficient. However, a final prediction will be needed if the deployed strategy are to balance the instantaneous power supply and demand for the grid. Second, stochastic models are preferable to deterministic models. There are always uncertainties in the driving force of building thermal load. For example, it is well known that the occupant behavior contributes significantly to the uncertainty of building operating conditions. This indicates that a deterministic prediction might be unrealistic. To reduce the derivation of the prediction caused by the stochastic nature, it is preferred to use stochastic models, such as probability-based models. There are three different methods to construct the models for B2G application. As shown in this table, we can categorize those models into black box, gray box, and white box model. So the level of understandings are increased from black box to white box. So here I want to point out three things for your attention. First, the prerequisite of using white box model structure is to have sufficient information for the studied system. As a comparison, the prerequisite for using the other two model structure is sufficient training data. Second, the formulas in the black box model structure may only make sense numerically as they contain no physical meaning. Therefore, they are not able to provide the insights for some studies. For example, obtaining the derivative information that is required for certain optimization algorithms, as we discussed earlier. This limitation does not apply to the white box model structure. Whether this limitation exists in the gray box model structure depends on the amount of information involved in the model construction. The third point is using the white box model structure ensures that the models have high fidelity. For other two structures, high fidelity is not guaranteed. The scopes of system modeling for B2G can be divided into two scales. At a small scale, it is used to study device-to-building modeling. For example, in the paper of Howell et al., they use the models to predict the zone temperature based on rated cooling rate of air conditioning. And then the rated cooling rate can determine the power demand by the air conditioning devices. The system model can also be applied to a larger scale, which is built into community scale. So this slide shows the study by Huang et al. So they studied the modeling of a net zero energy community by including the PV system, building thermal system, heat pump system, and domestic hot water system. After introducing all the concepts about modeling for B2G, now we will demonstrate how to apply the system modeling to the B2G with two case studies. The first case study is based on the paper written by Howell et al. They evaluated a transactive control strategy that realized demand response with a commercial building. Transactive control is a distributed control strategy to provide demand response by engaging various self-interested distributed energy resources. So we will show this in detail when we explain the case study. As we can see from the figure, the studied HVAC system serves an office building located in Pasco, Washington State in the United States. It consists of one chiller, one air handling unit, ducts, and 17 variable air volume terminals that provide conditioned air to offices and open spaces. The air handling unit is composed of one supply fan and one cooling coil. The ducts are equipped with 2 dumps to adjust the amount of exhaust air and fresh air. The control objective of this B2G control is to reduce the peak electrical power demand of the HVAC system, while maximizing the overall thermal comfort level of the zones during the cooling season. The optimization problem defined in this case study can be solved in a distributed manner with a transactive control strategy. The transactive control strategy creates 2 virtual markets, an air market with conditioned air as the trading commodity, and a local electric market with commodity being electricity. In the air market, each VAV terminal is a buyer, while the air handling unit is a seller. In the local electricity market, the chiller and air handling unit is a buyer, while the seller is the power grid. Since there is only one air handling unit and chiller in this study, so they are treated as a whole. We call it chiller plus air handling unit. To simplify the problem, the participation of the 2 markets, such as VAV and AHU plus chiller, are named agents. In each market, the agents are self-interested. For example, they tend to maximize the revenue from selling certain amount of resource at a high price, or minimize the cost by buying resources at a low price. As shown in the right figure here, each buyer agent expresses the amount of resource it is willing to purchase under the different price level with a curve. Here we call it demand curve. As we can see, when the price drops, then we are willing to purchase more. Similarly, the seller agents create a supply curve, the dashed line shown here, showing the amount of resource they are willing to sell at a given price. Then the market determines our equilibrium price, named clear price, which balances the supply and demand. After that, based on the clear price, each agent determines the amount of resource it will buy or sell at that optimal solution. At this stage, the demand and supply in the market will be balanced, and the market is considered to be cleared. The transactive control strategy can be implemented in a 5-step procedure. The first step is to create the demand curve for buyers in the air market, as shown here. So the right figure shows the demand curve is designed as piecewise curve, and is basically characterized by the 4 variables, P minus, P plus, Q plus, and Q minus. The slope between P minus and Q and P plus determines how sensitive the buyer agent are to the change of the price. For example, the steeper the price, the slope, the corresponding buyer agent is more willing to adjust its demand. To quantify the sensitivity, we introduce a parameter K in this formula to calculate the P minus and P plus for each buyer based on its preference. So here K, P0, and delta P are predefined parameters. The value of K is within the range from 0 to 1, and the larger the K is, the more willing the buyer agent will be to change the demand. The Q plus and Q minus represents the demand flexibility of the buyer, subject to thermal constraints and physical limits. In this case study, the buyer is the VAV terminal. The constraint is that the conditioned air should be sufficient to maintain the zone temperature within the control data band. The airflow rate should be also bounded by the minimal and maximal airflow rates provided by each VAV terminal. After we create the demand curve for individual buyers, the next step is to aggregate the demand curves for the entire air market. As you can see from this figure, the demands under the same price in all curves are summed to form an aggregated demand curve of the entire air market. This information will be provided to the local electricity market. In this case, the aggregated demand curve indicates the flexibility of the total demand for the cooling energy at the air handling unit level. It also expresses the sensitivities of the demand flexibility to the price changes. Next, we can move to the local electricity market. Here, the step 3 is to create the demand curve for local electricity market. In this step, the air handling chiller agent converts the aggregated demand curve for conditioned air in the air market to the demand curve for electricity in the local electricity market. The HU plus chiller agent converts the price information of the aggregated demand curve from the air market to the price demand curve in the local electricity market using this formula. So the P is the price of the conditioned air, and then the P elect is the price for electricity. So here we have our conversion factors. After that, the HU chiller agent converts the quantity from the air market to local electricity market by calculating the required electricity for generating a given amount of cooling energy. The step 4 is to clear the local electricity market. In this step, the local electricity market is cleared based on the received electricity demand curve from the HU plus chiller agent and a predefined supply curve, which represents the power limit. So for simplicity, the supply curve is defined as a vertical line in this study, as you can see here. In reality, the price may change with the power limit in other cases. The interaction of the supply curve, which is solid line, and the demand curve, which is the dashed line, shows that we are able to adjust the demand to meet the desired demand by the supply side at a cleared price for electricity, which is here. However, it is possible that there is no intersection if the building demand is too low or too high. For both cases, the studied system does have not sufficient flexibility to meet the desired demand by the supply side. As a result, the studied system will use default control set points, and there's no demand change caused by the B2G integration. After clearing the local electric market in step 4, the last step is to clear the air market. The clear price for the conditioned air is defined as P air clear equal to 1 over eta times P electric clear price. Meanwhile, the clear quantity is determined based on a curve defined in the demand curve for the air market. The temperature set point for the controlled thermal zone to realize the clear quantity can then be calculated correspondingly. So we introduced the concept of transactive control in the previous slides. Now we will see how we can apply system modeling in constructive control. It is actually used in step 1, 3, and 5. First, let's look at step 1, which is to determine the cooling demand subject to the thermal constraints. In this paper, the authors adopt a black box model that the future amount of conditioned air, Qt plus dt, is a function of current zone temperature, current outdoor air temperature, future zone temperature, and the current amount of conditioned air. Because this is a cooling scenario, we will achieve the highest amount of conditioned air if we set the lowest temperature bound. And similarly, we're going to achieve the lowest demand if we set the highest zone temperature. In step 3, we need to calculate the amount of required electricity for generating a given amount of conditioned air. We can calculate the chiller power by using the total cooling demand divided by COP and epsilon. And similarly, we can calculate the power required by the fan by including the discharged air temperature and mixed air temperature. Then we can sum up the chiller power and the fan power, get the total power. In step 5, we need to decide the corresponding temperature set points to realize the clear amount of conditioned air. Again, the authors used a black box model to calculate the temperature set point for the next time step, so with a given clear amount of conditioned air. After developing the B2G control strategy, the next step is to evaluate the B2G strategy. So in this study, the authors used the black box model to enable the transactive control, as we can see from the left, and then they developed a virtual testbed using Energy Plus, which is a white box model to mimic the real building. So the control signal will be generated by the transactive control sent to the virtual testbed, and then we run the simulation and get the system status as feedback to the transactive control. The virtual testbed, based on the white box models, can be used to validate the black box model in the transactive control. This slide shows the comparison of zone temperature predicted by different models. In the control setting, the control horizon length is 5 minutes and the K for each VAV terminal is 1. The parameters in equations of the black box model are determined based on the regression analysis of the simulation results from the Energy Plus, which is the white box model. The figure shows the validation results for August 20th. As we can see, the black box model is able to predict the room temperature in a good agreement with the white box model, which is Energy Plus. Based on the above procedure and models, the HVAC system with the transactive control is evaluated, and its performance is compared with the system without the transactive control. So in that case, it adopts a constant temperature set point of 21 Celsius degree for all the zones. The top figure shows the total power of chiller and the fans. As we can see, without transactive control, the peak demand is about 6.5 kilowatt around 1400 hours. With transactive control, the peak demand is restrained to 6 kilowatt and shifts to around 1000 hours. As a result, as we can see from the bottom figure, the transactive control continues to change the set points for VAV terminals, instead of a fixed set point adopted by the one without transactive control. To conclude this case study, we can see that system modeling can provide estimation of the building response, which is critical to realize the building-to-grid integration. System modeling can also provide the testbed for evaluating the performance of the building-to-grid integration. In the second case study, we extend the scope to communities. Here we conduct the evaluation with a simulated residential neighborhood consisting of 6 homes as shown in the figure. Based on their power usages, the homes can be divided into 2 groups, Group A and Group B. Each group contains 3 types of homes. The first type, A1 and B1, purely rely on the power grid to meet their power usage. The second type, A2 and B2, is equipped with a PV system. They use the PV system as a primary power supply and the power grid as their secondary supply. In addition, the actual energy generated by the PV will flow back to the power grid. The third type, A3 and B3, contains both a PV and a battery. This type of home will use the PV power as the primary power supply, then the battery as their secondary supply, and the power grid as the tertiary supply. When there is additional power from the PV generation, they will first charge the battery until it is full. After that, they will send the energy back to the grid. The objective is to study how we can resolve the dark curve problem by using storage technologies to store the additional power generated by PV panels and use it later. As we can see from the left figure, this is our power usage from the community, and this solid line is the power draw without storage after we consider the PV generation. Now we can see the famous dark curve. And then if we add the storage with control, then we're able to smooth the dark curve. The studied neighborhood is modeled using the Modelica Buildings Library, which is an open source library developed by Lawrence Berkeley National Laboratory. This figure shows the diagram of the Modelica models for the neighborhoods at the top level. As we can see, we have the power grid, AC power meter, and individual homes. This is type A1, B1, and then type A2, B2 has the PV panel. Type A3 and B3 has a PV panel and with a battery. In this study, a hierarchical modeling strategy is adopted to handle the model complexity. Take the model for home A3 as example. It contains subcomponent models such as battery, PV system, DC-AC converters, and also the battery charge discharge control. The inputs for the home model are the weather data through the weather bus and the power usage profile, and the major output is the power draw by the home. In this study, 2 power usage profiles for homes are adopted. So the profile A is obtained from literature which measured the power usage for home in California, United States. This profile is used as input for homes in Group A. Power usage profile B is generated by adding randomized deviation up to 15% to the power usage profile of A. It is used as inputs for homes in Group B. The PV system is sized to be 3.5 kilowatt, and in addition, the battery is sized as 3.5 kilowatt hour, and it can discharge until it is completely empty with the maximal discharge rate and the maximal charge rate at both set as 5 kilowatt. Now let's see the simulation results. In this slide, we can see that a good control of battery and PV can flatten the demand curve by using the homes A3 as example. The top figure shows the power usage and PV generation from this home. As we can see, the solid line is power usage by the home, and the dashed line is PV generation. The bottom figure shows the operation of the battery. The dashed line is the battery power. As you can see, if it's positive, that means it's charging, and if it's negative, that means it is discharging. The solid line shows the status of charge, or SOC, for the battery. As we can see that in the early morning, the SOC is 0 because all the energy stored in the battery was used in the previous night. Then the battery starts to charge when there's additional power from the PV, and then it starts to discharge around 1700 hours when the PV generation is less than the power usage. The results for home A3 indicates that aiding a battery smoothing the dark curve as expected. However, when we aggregated the power draw by the entire neighborhood, we can still observe the darker curve, as we can see shown in this figure, since only a few homes are equipped with energy storage and control. To solve this problem, we may consider two options. The first is to enable the interaction between homes so that energy storage can be shared by all homes. The second is to utilize the home as a virtual battery. The first option requires a mechanism to coordinate the allocation of stored energy for all homes and to achieve the desired power draw at the neighborhood. Depending on the diversity of the power usages, finding the optimal allocation that minimizes the negative impacts on the operation, such as voltage stability, can be challenging. Potentially, we can use game theory to solve this problem. On the other hand, the second option uses the power flexibility of each home by charging and discharging its virtual battery. To do so, however, the power flexibility of each home needs to be quantified so that we are able to accurately control the amount of stored energy. Building models can be used to serve that purpose as discussed in case study 1. As a summary, this seminar discussed what is building-to-grid integration, or B2G, and why B2G is needed. We also reviewed the modeling needs for B2G in the design, evaluation, and deployment phases. We then discussed 3 types of system modeling: black box model, gray box model, and the white box models. As we know, the scope of modeling can vary from device to buildings or buildings to communities. And then we demonstrate the application of system modeling in B2G by using 2 case studies. In the first case study, we discussed the transactive control for HVAC system. In this case study, we use black box model for control and then white box model for evaluation. In the second case study, we evaluate B2G control strategy with energy storage, and here we use the white box model for the evaluation. If you are interested in this topic, besides reading the book chapter, you can also read the following papers and reports. If you have any questions, feel free to contact me or any of my co-authors. So our email is given here. Thank you for your attention. I wish you have a good day.